All right, welcome back. Mr. Jorgens here. 6.2, we're talking about radicals and rational exponents. Today, part 1 is going to be all about radicals, and then part 2 is going to be all about rational exponents. So we're doing radicals today. Make sure you stay tuned for learning. Radicals is another word for that is square roots. So we're going to learn about square roots today. So a review from past years is we kind of learned about inverse operations between squares and square roots. And what I mean by that is 4 squared. We know that kind of means 4 times 4, which is 16. And then if we had taken the square root of 16, we could think, oh, 16 is 4 by 4, so I can undo that square root by thinking the square of 4 is 16. So the square root of 16 would be 4. So whenever we're doing a square root problem like square root of 16, I'm trying to think of what number multiplied by itself would equal 16. In this case, 4 multiplied by itself would be 16. So then the square root of 16 would be 4. And so it kind of takes that 16 and goes backwards and thinks about what would the square be to make 16. Those are called inverses in math. Addition and subtraction are inverses. Multiplication and division are inverses. And squares and square roots are inverses. So we're going to think about an example here of these. And starting out, I'm going to do a few of these really quick. I'll call it example 1a. If we had the square root of 4. I'm thinking square root of 4, what would make 4? 2 times 2, right? 2 times 2 would make 4. So because 2 times 2 would make 4, in a way I can think of it as the square root of 2 squared. I can think of it as the square and the square root are inverses. They undo each other, and I'm just left with 2. So let's try another one, square root of 81. If you think about it for a second, I'm thinking of all the things that can multiply to 81, but I'm only thinking of like the same number and itself. So hopefully you're good with things like 12 and under, and 81 would make 9 and 9, right? 9 times 9 or 9 squared would make 81, and then the squared and square root are going to undo each other, and so I'm left with 9, right? So 2 would be the square root of 4, 9 would be the square root of 2. You go ahead and try this one, square root of 49. What would that make? Enter your answer when you're ready. Yeah, so 7 times 7, right? Square root of 7 squared. So the square root of 49 would be 7. One more for you to try here. Square root of, let's do 36. Go ahead and try that one. Enter your answer when you're ready. Yeah, so 6 times 6 is 36, so square root of 6 squared. And I'm left with 6 as my answer here. Now, we don't just have square roots in math, although those are probably the ones you've seen before. We can also do cube roots, fourth roots, fifth roots, and etc., right? And so we're going to start talking about some of those today. Now, how a cube root comes about is we don't just have squares. So like, let's say instead of, last time I talked about 2 squared or 2 times 2 or 4 squared, 4 times 4. Let's think about 4 to the power of 3. I call 2 to the power of 3 a cube, right? So if I ever have a 3 up here in the exponent, I'm thinking of cube, that's my word for it. And what that means is 4 times 4 times 4. 4 times 4 times 4. If I multiply those together, 4 times 4 is 16, and 16 times 4 makes 64. So if I had 4 to the power of 3, that would make 64. Similarly, I could have a problem that looks like a square root, where I have 64 on the inside. If I had square root of 64, that would be 8, because 8 times 8 makes 64. However, if I had this little 3 here, we call that the index number, so the index of the square root. If that index is there as a 3, that means I'm looking for some number that times itself 3 times, or the cube of that number would make 64. In this case, if I just did it, right? 3 4s multiplied together is going to make 64, or 4 cubed, right? So that cube root in the index of 3 undo each other, and I'm left with 4. Right? So this is kind of like a new thing. If I have an index number, and again, my index number, when I'm saying index, I'm talking about this number on the outside here. Square roots would have no index, and that automatically means 2. But now if I have, like, let's say I have the cube root of 8. Now that means I'm looking for some number that multiplied by itself 3 times is going to make 8. And so you're going to have to be a little bit smart or clever about thinking about what number that could be. So in this case, 2 times 2 times 2. 2 times 2 is 4. 4 times 2 makes 8. So the cube root of 2 cubed. So again, then the cube root of 8 would make 2. And you should be able to see how these things kind of go back and forth, right? Like 4 to the power of 3 makes 64. And so then working backwards, right? The cube root of 64 would be 4. They're inverses. We wouldn't just have cube roots, though. We could also have like 4th roots. If I had the 4th root of 81, for example, I'd be looking for some number that multiplied by itself 4 times could make 81. And sometimes as you get to bigger numbers, it's helpful to make what's called a tree diagram for these. And the way a tree diagram works is I'd be thinking of 2 numbers that multiply to 81, which from the previous screen we had as 9 and 9. And then I could break that down further. 9 is 3 times 3. And since I have a 4th root, I'd be looking for 4. So I have a group of 4 3s here. So 3 times 3 times 3 times 3. And again, then the 4th root of 3 to the 4th would just be 3. So that's kind of how we'd go about calculating roots that are bigger than just square roots. So again, if we could have a 3 as the index, a 4, a 5, you could have a 6th root, a 7th root, whatever root that is, that's just going to be the index number. And that's going to be how many numbers you'd have to have inside the square root in order to pull 1 out. All right, let's try another example. Here's one for you to try. It's based on what we just did. We're looking for the 3rd root of 27, so some number multiplied by itself 3 times to make 27. Go ahead and calculate that and enter your answer when you're ready. So I drew out a little tree diagram on the right here. 27 breaks down into 9 times 3, and then 9 is 3 times 3. So I have 3 3s kind of multiplied together here. So I have essentially on the inside 3 times 3 times 3. So I have one group of 3 3s. So I know that the cube root of 27 is then just 3. And that should make sense because 3 to the 3rd is 27. Therefore, the cube root of 27 would then be equal to 3. They're inverses. Go ahead and try one more. Let's do the 5th root of 32. That should make things interesting. 5th root of 32, think about that one. Enter your answer when you're ready. So making my tree diagram, I have some different options for 32. I'm going to pick 8 times 4. If you wanted to pick 16 times 2, that would work. And then again, I'm going to pick 8 and 4 is 2 and 4 makes 8 times 4. And you might be tempted to circle the pair of 4s there. And that would make sense because usually in square roots you would circle the pair, but in this case I need a group of 5 because my index is 5. I'm looking for a 5th root. And so I'm going to have to break my 4 into a pair of 2s and then my other 4 into a pair of 2s, and then I'd have 5 2s. And then now I'm in business, right? Because I have the 5th root of 2 times 2 times 2 times 2 times 2, 5 2s all multiplied together. So then I can take that one group of 5 2s and I'm just left with 2. That should make sense. Again, I have 2 to the power of 5 is equal to 32 because 2 times itself 5 times makes 32. Therefore, the 5th root of 32 is going to be equal to 2 if I undo that as an inverse. The last thing we need to talk about is what happens when a square root doesn't go in evenly. And example 3 here is going to be a case where it doesn't go in evenly. There's going to be a part A and B. A I'll do and B you can try. Now, square root of 75. Again, there's no number on the index. And again, my index, if there was a number, would be right here. Since there's no number there, that means it's kind of like an invisible 2. So I automatically know I'm looking for pairs in my tree diagram. Now, the problem is there's no number that if I times it by itself, it makes 75, right? And I know that because 8 times 8 is 64, too low. And if I try one higher than 8 and go to 9 times 9, so 8 times 8, 64. 9 times 9, though, is too high. That's 81. 75 is somewhere in between. Since 75 is somewhere in between, I know that it's not going to go in evenly. So when I do my tree, I'm going to have a number left over. How that's going to look is 75 is 3/4, right? 3/4 makes 75 cents. So 25 times 3 makes 75. And then 25 can split into 5 times 5, right? And those are all prime numbers. They can't be broken down further, the 5s and the 3s. I have a pair of 5s, but this 3 is left over. It doesn't have anywhere to go. So what I'm going to be able to do is I have a pair of 5s. I can take one 5 to the outside, but my 3 doesn't have any pair. I can't undo 3 by its square, so I have to leave it on the inside, and I have 5 square root of 3. All right, so that's kind of the way these ones are going to go. If you're ever doing a problem with square roots, anything that gets circled as a pair has a partner, it comes to the outside, right? So circle here goes on the outside of the root. And anything that doesn't have a partner here, the 3 stays by itself and it goes on the inside. So last little one for you to try. Here we're going to do the square root again, this time of 72. So go ahead and try that one and enter your answer when you are ready. So if I work out 72 here, there's kind of a couple ways of doing this. I think the easiest way is just go 36 times 2, and then 36 breaks into 6 times 6. So I have that pair of 6s that comes to the outside, and then I have that 2 left alone that's going to stay inside the root. So you should be left with 6 square root of 2. All right, hopefully that's a good starter, part 1 of section 6.2. I got another video coming at you here that'll be part 2, where we'll cover the fractional exponents.